The manganese content in a 12-gram sample of steel was determined by measuring the absorbance of permanganate MnO4- using the following process. Let's revise Year 12, Module 7. What color is permanganate? It's an oxidizing agent. Purple. When you oxidize it, it turns into the manganese ion, Mn2+, which is clear or colorless. Good. What homologous series do you use the oxidation test for in Module 7? Alcohols. Which alcohol out of primary, secondary, tertiary doesn't oxidize? Tertiary. So it would stay purple. Awesome. Well done. That's just Module 7 revision. The still sample was dissolved in nitric acid and the Mn2+ produced was oxidized to MnO4- by periodate ions IO4- according to the following equation. They've given you the equation. The resulting solution was made up to a volume of 1 liter, then 20 mils of this solution was diluted to 100 meters. You know now, you've been scarred from your previous questions to be wary of any volume changes. Normally, they dilute it and da-da-da, but then when they ask you the question, they want the amount back in the original sample. The absorbance at 525 nanometers, if you're doing a calibration curve, you would have already set it at a known wavelength. In this case, they've done 525. Of the resulting solution was 0.5. And they've given you a calibration curve and they're asking you what's the percentage by mass of manganese in the steel? Okay. They've done their standard solutions with known concentrations of MnO4-. They got a relationship between absorbance and concentration. And for their unknown solution, it had an absorbance reading of 0.5. So what we do now is we go, hey, we know the relationship between absorbance and concentration. That's plotted in the graph. So then if one of the absorbances happens to be 0.5, I find that on my y-axis, do my dot, 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 go down to my x-axis, and then I realize, oh, an absorbance of 0.5 corresponds to a concentration of 25. And then with these questions, you have to be careful of the units. So let's make a note here. At an absorbance of 0.50, the concentration on the x-axis is 25 milligrams per liter. Okay. All right. We have to keep track of the volume changes because when we were reading, it changed quite a bit. Yeah. There's no volumes in the first half of the question where the above the equations we're watching here. All right. Tell me, we'll read it from start to finish and then we'll work backwards after. What is the first volume that your sample went into? One liter. The resulting solution was made up to a volume of 1 liter. And then what happened afterwards? What's the next volume that it went into? What's the next volume that it turned into? 20. So they started with an original 1 liter, they took 20, and what happened to the 20? It turned into what other volume? It turned into our 100 mil volume. And then that's the final one. There's no volume change after that. And then they said the absorbance of the resulting solution was 0.5. So what that means is they did the test with the 100 mil sample. All right. But they want the original steel sample, which means we have to work our way back up. So this concentration that we've got at the moment is the 100 mil sample that they ended up turning the original into. I have to work my way back. I could change the concentration I could figure out what the concentration is in 20 and figure out what the concentration is in 1 liter. But guys, did the question want concentration? Or does the question want concentration? What's the variable that they actually want? They want mass. Yeah. So there's really no point in me working with it in terms of concentration. I might as well get rid of the per liter part now and change it into mass because that's where I want to be at the end. So so if it's 25 milligrams per liter in 100 mils, 25 milligrams per liter times 100 mils is zero point 0.1 liter, gives me 2.5 milligrams. Okay, so I'm starting to work with it in terms of mass. I haven't changed the amount that's actually in the solution. I've just expressed it differently. So if the concentration is 25 milligrams per liter in 100, then in 100 mils, there's 2.5 milligrams. So 2.5 milligrams in 100 mils. And I'll do my conversions with this because that's what the question wants. They want mass. So that's the amount I have in 100 mils. The question started at 1 liter, they went to 20 mils, then they went to 100 mils. I want to go back, yeah? Because the question asked me for the original. What did the question do to go from 1 liter to 20 mils? I'm working with it in terms of mass. If I had 1 liter and then I scooped out 20 mils, is the mass in my 20 mils smaller or the same as in the total 1 liter? Think of mass as amount. I have a certain amount of chemicals in 1 liter and I scoop 20 mils. Will my 20 mils have the same amount as before? Yes or no? Yeah, the mass will be smaller. There's no way you could possibly scoop all of the mass in 1 liter in 20 mils instead. So when you went from 1 liter to 20 mils, the mass in the 20 mils is smaller. There's going to be a smaller mass. But we have to figure out how much they actually divided the mass and the volume by. So we have to do it in the same units. 1 liter to 20 mils. 20 mils is 0.02 liters. How many times, what did they divide 1 liter by to turn it into 0.02? How many times did they divide up the volume? It's like 50? 1 divided by 50. Yeah, 50. Okay. For them to go from 1 liter to 20 mils, they divided the volume by 50, which would have divided the mass in equal parts of 50 as well. Okay. And from 20, what did they do to go to 100? They diluted it. Diluting means you add what? You're adding water. And if you're adding water, so if you add water, yes, the volume goes up, but you can think of it in so many different ways. We're currently thinking of it in terms of mass. If they added water, did the mass from 20 to 100 change? No, all they did was add water. If we were thinking about it in terms of volume, then yeah, we'll talk about changes, but mass stayed the same. Okay, so that's what the question did. Now I have to trace the steps back. From 20 mils to 100 mils, the mass stayed the same, which means when I go from 100 to 20, what do I do to mass? Nothing. It also stays the same because I'm just tracing it back. Now, from 1 liter to 20 mils, the question divided by 50, which means from 20 back up to 100, I times by 50. Yeah, I'm just tracing back the steps of the question. Okay, good. I'm currently at 100 mils. So we said the mass stays the same when it goes to 20. So it's 2.5 milligrams in 20 mils. And then you said the question divided by 50 to go from 1 to 20 mils, which means when I go back, I have to times by 50. So times by 50 times by 50. 20 mils times 50 is 1,000 mils, which is 1 liter. 50 times 2.5 milligrams. What's the mass in 1 liter? 125. Thank you. Good. I've gotten back to the original scenario. Awesome. What you normally do here is you just do whatever the question wants because you've got the correct scenario now. However, what's the chemical in the graph? What concentration have we been working with the whole time? MnO4 minus. What chemical are they asking you for in the question? Just the manganese. Okay, so this is actually an added layer from the questions you're used to. You normally just do volume changes with the same chemical. You've done volume changes now, but they don't even want that chemical. You've got MnO4 minus. They want manganese. You've done all of your volume changes, that's great. We're not at the end though. You've got permanganate, but they want manganese. You relate different chemicals together via a chemical equation. You always have to do it that way. And chemical equations get read in terms of moles. Okay. So you've worked with it in terms of mass so far because you've been dealing with the same chemical every time. But if you're going to use the equation to relate MnO4 minus to Mn, you need to do it in terms of moles because 125 milligrams of MnO4 minus is not the same as 125 milligrams of Mn. Okay, so you've got the correct volume now. That's great. But I need to get to my manganese. So moles of MnO4 minus is mass on molar mass, which is 125 milligrams, which is 0.125 grams. What is the molar mass of manganese, please? Manganese is in the transition metals section of your periodic table. Thank you. 54.94. Okay. And then plus 16 for each oxygen, and there's four of them. What is the number of moles of the permanganate, MnO4 minus? 0.00105, thank you, mole. And then I can relate it to the other chemical, Mn, that the question actually wants. So have a look at the ratio. What's the moles of Mn going to be if you currently have the moles of MnO4 minus? It's going to be the same. Good. A 2 to 2 ratio is the same as a 1 to 1 ratio. So the moles of Mn is going to be the same. So that's the 0.00105 mole. Okay, good. That's in your same original 1 liter. because you already got to the correct volume, you just now have to get to the correct chemical, which is good. So you've got the correct volume, you've got the correct chemical. So now you can do what the question wants with said chemical, and they want you to get mass. Okay. Now, guys, I know you had mass before, but it was mass for MnO4 minus. You can't go from mass of one chemical to mass to the other. You have to do moles and then convert back to mass afterwards. It sounds redundant, but it will not give you the same answer. You can't do it. Okay. So mass of Mn2 plus moles times molar mass 0.00105 mole. Now that I'm only doing Mn2 plus, I only take the 54.94. Take the molar mass for whatever formula you're working with now. 54.94 grams per mole. What is the mass of Mn2 plus, please? Point oh 57687 grams. You've got mass. You've got manganese, you've got it in the original sample, and they want percentage by mass, which means percentage out of the whole thing. And the whole sample, they actually gave you the mass at the start, which was the total 12 grams. So as a percentage, you've got the smaller mass over the entire mass. And for you to turn it into a percentage, you times by 100. What is your percentage of the total 12 grams? 0.48%. Good. So your answer is going to be C. Okay. So reading the calibration curve itself is really straightforward. There are additional things that they do to the solution to prepare it for the calibration curve, which means normally they ask you for the original sample, so you have to do a bunch of volume changes and unit changes afterwards. Okay, but reading the graph itself is straightforward.